Okay, so we talk about hash function. So hash function, it is taking any bit input, a message, long message, and it has to give us the hash edges. So let us talk about some background of this hash function, where from it is coming. Basically, it is to solve a problem which is called symbol table problem. So in a symbol table problem, what we have few records. It's basically a database problem. We have few records, and we need to store that record in a table. So basically, each record has some entity, like student record, your roll number of a student, your name, so your CGPA, your address, so on. So this is a record, and this X is a pointer to this record. So among this field, we choose one field as a key. So that should be unique to that record. So maybe roll number, for this purpose roll number can be the key. So this is a key of X, because key roll number is unique to each student. So among this field, each is a key. Now we have such n records, and we need to store the record into a table in a this is a dynamic set. So we need to store the records. They say there are, at some point of time, there are n records in a table, such that we should perform some dynamic operation like insert. We should able to insert a record in a table which is not there. So we should able to insert a record. We should able to delete a record from the table. Okay, a record is there, we can delete a record. Suppose student pass out, so we should delete that record from the table, and we should able to, these two are dynamic operation. And then main important thing is we should able to search a record. So we should give a key value. So key is the k. So we should able to so corresponding that record we should able to get. So this is the search. We should able to search whether that record is, that key value is there or not. Okay. So these are the operation we can do. So we need to have a data structure. We need to have a data structure for this. So first we can think of a array of doing this. Array data structure for doing this. Suppose we have a say record, say we have some records whose key values. So this is our dynamic set S. This is the record. So this is T. Suppose we are just having, say, 4, 6, 9, 2. So these are the key value corresponding to that record we have at some point of time. So what we can do? We can have a, so say 6. This is a 5. So we can have an array of size 6. 1, 2, 3, 4, 5, 6. We can have an array of size 6, and then if a record is present, we will put it 1, otherwise we will put it 0. Okay. So this is just a direct access table, or just a bit vector. So this is very simple, but it is a very powerful data structure. But there is a problem with this. Problem is, if we have a key whose value is bigger, suppose we have, instead of 2, suppose we have a record whose key value is this. Okay. Our number of record is less, but the value of the key of a particular record is big. So in that case, we need to maintain the array of this much size. So that is a unnecessary uses of memory. So that is the drawback of this simple array representation. So to solve this problem, what we have the function which is called hash function. So hash function is a function from, so this is a set of all records, set of all keys. So this is universe of keys. Universe of keys, that means set of all possible keys, all possible keys. So this is this set. So this is all possible keys we have, and we have a fixed size, table size fixed. So, we have a table size of fixed length, say the table size is 0 to m minus 1. So, we have total m slot. So, this is basically an array, but table size is fixed, array size is fixed. So, it is a m size array 0 to m minus 1. In C language we use 0 to m minus 1. Okay. So, then any function h which is from set of keys to this is called a hash function, is called a hash function. Okay. So, any function from it taking a key and it is applying the hash value, hash of h of this, and it is putting into some slot. So, this is a 2. So, h of k is 2 like this. So, say we have a key 512. So, it is applying the hash function on 512. So, it is storing into the 10th slot. So, h of 512 is 10, something like that. Okay. So, it is basically a function which is taking a key of, key could be any arbitrary length, and this could be a very fixed size, smaller size. Okay. So, it is just a mapping from this key to the slot, it is hitting a slot there. So, this is called hash function. Now, there is a problem with this method, what is called collision. Okay. Suppose we have this situation. Now, we want to apply this 312, and suppose we apply 312 and 312 is also hitting here. So, h of 312 is also 10. So, 10 which is same as h of 312. So, this is possible very much, because h is a function from a to b. So, this is a set, this is a means set of universe a, and this is b set, very small set, because number of slot is very small. So, there has to be collision, because it cannot be a bijective mapping, it cannot be a injective mapping, because these two sets, this is a very smaller set than this one. So, there has to be many keys which are mapping to the same slot, and this situation is called collision. And there has to be collision. Okay. We cannot avoid that, because this domain is much bigger than the codomain. Okay. So, now the question is how we can handle this collision, because if two points are mapping to a same slot, we cannot fit these two keys there, because each slot is a room for capable to store only one key. So, what we do? We can have a chain. So, here two keys are colliding 512, 312 in the 10th slot. So, what we can have? We can have a chain or linked list. This is called chaining method. Chaining. Okay. So, we can have a chain which is just if in a slot, if more than one keys are colliding. So, we will put in a linked list. Okay. So, this is the hash function. So, this way we will store our keys. Okay. So, suppose we have a this is a set of universe of keys. Suppose we have, this is our key set we are interested, and suppose there are n keys k1, k2, kn, and we have this hash table. Okay. So, now we apply the hash function and we put it into the table. So, each of this. Now, in the worst case, it may happen that all the keys are going to the same slot. So, all the keys are going to the same slot. That may happen. So, if that is the case, that is called worst case. In that case, what is the search time? If you have to search a key and if it is hitting to that particular slot, we have to read the whole list. So, that will take a linear time. So, that is the worst case, but if we assume our hash function is good hash function in a sense that it will distribute the key uniformly among the slot. So, some sort of uniformity is there, uniform distribution of the keys among the slots. Then we called our hash function is good hash function. That means, we take a particular key, then it will go to the any of the same slot with probability 1 by m. So, it is equally likely. So, keys are distributing very much uniformly over the slot. So, that means probability that ki is going to the jth slot is basically 1 by m. So, each slot are equally likely for to fit a key. So, other way also. So, it is just a uniform distribution of the key among the slot. So, in that case, if there are m slots 0 to m minus 1 and if there are n keys, so if n is the number of keys at some point of time and m is the number of slots, then we define n by m, which is basically alpha, which is basically. So, we have n keys, we have m slot. So, n by m is the expected number of keys in each slot. So, if we have say 10 slot and if we have 100 keys and if our hash function is a good hash function in that sense, then it is uniformly distributing the keys among the slot. So, each slot will be having roughly n by 10, this is n by m, this is basically 100 by 10, 100 keys. So, this is called, this is the expected number of keys per slot, if our hash function is good hash function in a sense that it distributing the key uniformly among the slot, expected number of keys per slot, and this is called load factor. This is called load factor. Okay, so now if we have this, if your hash function is good hash function, then how much time we will take for searching a key? How to search a key? So, we want to search a key k. So, what we do? We have to first apply the hash function. So, then one hash function is required, then we reach to the slot, and in that slot we are expecting alpha number of, we have a chaining method because alpha is the number of keys colliding there. So, we just have to read that, scan that list. So, that chain. So, that will take this many times. So, this is the time for searching if our hash function is distributing the key uniformly. Okay, so this is the analysis of the chaining method. Now, we will talk about how we can construct a hash function, some example of hash function. Some example of hash function. Okay. So, first method we will discuss is called division method. Okay. So, suppose we have a our keys are integer, and our table size we choose m, usually we choose m to be prime. Now, so keys are integer, so hash function on this key is basically mod m. So, this is the set of integer. So, we have a fixed size hash table 0 to n minus 1. Okay. So, k is any integer of arbitrary length. So, this could be say m could be say some fixed length 3 bits. Okay. So, that means maximum value of m is 2 to the power 3 8, and this could be any size 5 on 2 bit, any length integer. So, we just map into the fixed size. So, anyway, this is the operation, mod operation. So, if you take the mod m, it will ultimately give us a remainder will be the integer from 0 to m minus 1. So, it will hit a slot there. So, this is the division method. Now, in this method, instead of choosing m this, if we choose m is equal to 2 to the power m, 2 to the power some r, then there is a serious problem with this method. If we choose this, suppose we have a key say like 1 1 1 1 0 1 1 0. Okay. Suppose key is say 2 to the power 7 bit. Key is 7 bits say. So, 1 2 3 4 5 6 7 8 9 10 11 12. Suppose key is 12 bits each key. So, this is a particular key. Now, if we choose m is equal to say 2 to the power 5, 2 to the power 5 means 1 2 3 4 5, this one. So, what is the, in that case what is the k mod m? K mod m is basically this one. So, we do not so these are the high significant bit. So, high significant bits has no contribution with this hash value. So, that means if we change any of this position, it will give us the same hash value if we fix this bits. So, there are lots of collision there. So, any change over here. So, there are how many bits 1 2 3 4 5 6 7. So, 2 to the power 7 bits are colliding, 2 to the power 7 keys are colliding into a particular slot, which is this, and this is a huge number of collision is happening over here. So, that means this hash function is not distributing the key uniformly among the slots. So, this is not a good choice. M is 2 to the power r is not a good choice. So, we avoid this in order to having more collision. So, we want our hash function should distribute the key in alpha way, load factor way. So, that is not happening over here. So, usually for this method we choose m to be prime, which is not close to some 2 to the power r, or if you are in decimal system at 10 to the power r, or if you are in octal system or hexadecimal or like this. So, this should not be close to this. Okay. So, to avoid this problem, we have the second method, which is called multiplication method. This is one example of hash function. So, another example is using the multiplication method. Okay. So, in this case we are allowed to choose m to be 2 to the power r. So, we are taking m is 2 to the power r. Okay. And suppose our computer words are w bit. So, our key is w bit, binary bits. Okay. Now, we choose a constant a, which is also a w bit. So, this is a constant we are choosing. So, now what is hash function h of k? What we are doing? We are multiplying a with k. So, if you multiply a with k, so this will be a is w bit, this is w bit. So, this will be 2 w bit. Now, we want to make it again w bit. So, we will do the mod 2 to the power w. So, then it will give us a w bit, but now we want this to be r bit, because m is 2 to the power r. So, then we will do the right shift by w minus r bits. So, this is the hash function. h of h of k. Okay, so we will take an example how it is give the values. So, let us take an example for this. Suppose m is 8, which is basically 2 to the power 3, and our w is say 7. Okay. Now, we take a. Suppose a is 1 0 1 1 0 0 1. This is a. We have to choose a constant of 7 bit. So, this is a we are choosing. Now, we have to choose a k for on which we have to apply this hash function. So, let us take a k 1 1 0 1 0 1 1. This is our key k. So, now we have to apply h of k is by this formula. So, we have to do the a into k. So, if you do this, then we will be getting a 2w bit, that means 14 bit. So, 1 0 0 1 0 1 0, then 0 1 1 0 0 1 1. So, this is basically a into k. Okay. So, this is just a 14 bit. Now, if we want to make it 7 bit again, so we are taking mod 2 to the power 7. So, this will give us only this. This is mod 2 to the power 7. Now, this we want to apply the left shift of w minus r. W minus r means w is 4 times we will do the left shift, sorry, right shift. So, if we shift, this is gone, this is gone, this is gone, this is gone, only this one is left. So, this is basically our h of k for this k. Okay. So, this is the multiplication method, and here we are allowing the h to be m to be 2 to the power r. Okay. So, now we will talk about there are other example of hash function we can discuss later on. So, now we will talk about how to handle the collision without having a extra storage, without having extra, I mean we are not allowed to do the chaining, because we are not having extra memory. So, that will be handled by what is called open addressing. Open addressing, this is to handle the collision. We cannot say there will be no collision in the hash function. Collision will be there because domain size is bigger. So, one way of handling the collision we will know, that is the chaining method, but in the chaining method we need to have a chain in the outside the table. So, extra storage is required. So, in this, suppose we have no extra memory, no extra storage. So, everything we need to do inside the table. So, only everything we need to do inside the table. So, how we can handle that? So, we are not allowing to make the chain, we are not allowing to have the linked list outside the table. So, everything we need to do into the table. So, that is the thing. So, that is addressed by the open addressing. So, that is called open addressing method. So, here what we have a table of size n, sorry, m minus 1, and say we have k many hash function, we have n keys, and here our hash function is basically it is we have a family of hash function basically. We have family of hash function. So, we first apply the, so this is the probe number. So, this is first probe or the 0th probe. So, we apply the, suppose you want to insert a key which is 512. So, suppose it has some keys over here 311, 612 like this. Okay. Suppose we insert 512, we have some other keys. Now, we first we try for the first probe. So, this is basically H0 of 512. We have many hash function. So, suppose it is hitting here. So, H0 of 512 means 1. So, this is not empty. So, we cannot put it there. So, it is occupied. So, then we have to go for the next try, we have to go for the next hash function. So, that is the next probe. So, 5 1 2 1. So, this is the next hash function. Suppose again, so this is first probe or the first again, suppose this is hitting here. So, this is a fifth slot and which is occupied by somebody else. So, this is not empty. So, next suppose we have to go for the next probe 5 1 2 2, this is another hash function. Now, suppose it is giving us some empty slot. So, this is the second slot 5 1 2. So, this is we fit it there. So, this is the way. So, we have a collection of hash function. So, we will keep on searching the empty slot until we succeed. So, every time this is the probe sequence we have to follow. So, we first apply the H 0, the first so we have collection of hash function. So, first probe 0th probe we will apply this one, if it is hitting a occupied slot we will try next one, next probe like this until we reach to a until we hit to a empty slot. Once we hit to a empty slot we will store it there. Now, deletion is a problem with this, because suppose so it is hitting first, it is hitting here, next it is hitting here. Suppose we deleted this 3 1 2. So, 3 1 3 1 1 or something. So, we deleted this and we make it this slot empty. So, what we will do then after that, suppose we are finding 5 1 2, we want to find 5 1 2. So, we will follow this, we will apply the first probe or 0th probe, it will hit to here, then we apply next probe, it will hit to here, but we see this is a empty slot. Then we may report that 5 1 2 is not there, but that is wrong. So, somehow we need to have some information over here. This room was originally not empty, somebody was sitting here, he or she has died. So, this room has some, so some sort of tag we can need to put that some keys were there, this room is not from the beginning empty, somebody was there. So, we put a tag over there, so that we can go for further probe to get the 5 1 2. So, that is the deletion we need to handle. Okay. So, now let us analyze this probing strategy, open addressing strategy, and then we will take some example of a probing. So, first example is linear probing. So, in linear probing it is basically ith probe is, so h of k plus I mod m. Okay. So, it is basically, so we have the hash function h, we will apply h, and if it is okay, so we have a key, so we apply h on that. So, 0th probe, so this is the ith probe. So, for the first probe or the 0th probe, what we are doing, we are just applying h of k mod m. So, it is hitting somewhere, if it is not free, if it is not empty, then we will go for one probe. One probe is basically, first next probe h of k plus 1 mod m. So, we will look at the next, so this is hitting, so we will look at the next slot, and if it is not empty, then we will look at the next slot, that is k 2 like this. So, we are just looking at the serially like this. So, next slot whether it is empty or not. So, this has a problem of clustering, if it is hitting an occupied slot, it will just put it into the next. So, there is a clustering with this with these slots. So, this is not uniform distribution among these slots. So, that has a problem with this. So, next is, so to avoid this problem we will apply what is called double probing. So, in the double probing, so So, this is the jth probe. So, we have two hash function mod m. So, what we are doing? So, 0th probe h of 0 is basically we are just calculating h of k. If it is hitting to a occupied slot, then we go for the next probe, which is basically h of k, h1 of k plus h2 of k. So, we have another hash function we are adding, then mod m obviously. Then again if it is hitting, so we will go for the next probe, but we already calculated these two value. So, we will just do this mod m, this way we will check. So, this is better than the linear probing to avoid the clustering. So, let us just quick analyze the this open addressing. Okay, so now if you have a open addressing method to solve the collision, then suppose there are n keys, n is the number of keys and m is the number of slots. So, for open addressing obviously n must be less than m, otherwise we cannot handle everything into the table, we are not allowing any extra storage. So, this is a theorem, it is telling us the expected number of probes for an unsuccessful search. Is equal to is less than equal to 1 by 1 minus alpha. Alpha is the load factor. So, we need to prove this. So, how to prove this? So, suppose there are n keys. So, one probe is mandatory, we need to apply the hash function, one probe is mandatory. Then when we will go for second probe, if it is hitting to a occupied slot. So, what is the probability that it will hit to a occupied slot is basically n by m, because m is the total number of slot, that is the total number of cases, and n is the total number of keys which is occupied in the slot. So, it will hit to a slot which is not empty, means just the classical definition, and then again we will go for the next probe. Now, again when we go for the next probe, if it is hitting again a occupied slot, so that probability is this. So, this way we continue. So, this is basically less than, so we can use this m minus I is less than basically 1 by m. So, if you do this and this is alpha, so we can just write this less than equal to 1 plus alpha into 1 plus alpha into 1 plus alpha, so on, 1 plus so on. So, this is basically less than equal to 1 plus alpha square, so on. So, this is 1 by 1 minus alpha. Okay, so, this is 1 by, now if our table is half full, that means if alpha is 50%, alpha is half, then what is 1 by 1 minus alpha? It is basically 2. So, that means if the table is half full, we need only 2 probes for an unsuccessful search, but if the table is 90% full, 0.9, then we need 10 probes to get a unsuccessful search. Okay, thank you.